And welcome back. This lecture is going to be a pretty short one. A lot of this we've covered a bit already when we did the lecture about sound and properties of waves, particularly with sound. This is going to focus on the same stuff but with light instead. Our goal for today is to understand reflection and refraction. In other words, what happens when light hits the surface. Objectives, we'll look at reflection off a simple mirror. We're going to look very briefly about scattering. We'll look about refraction, mirages, which is related to refraction, rainbows, and then we'll learn about total internal reflection, which we've already covered. So, when a photon meets a surface, a few things can happen. There are three main things that can happen, and some of these other ones are subsets of those three main things. The first thing that happens is reflection. The light bounces off of that surface, kind of like when light hits a mirror. When light bounces off the surface, the angle, the reflected angle, and the incident angle are equal. Now I have to define incident angle here. If I have an object, let's say a mirror, the perpendicular to that object at some given surface is the incident. The angle with respect to that is the angle of incidence. So this is theta I. So the light is going this way. So I have my light bulb over here. That light will reflect such that theta R equals theta I. So the angle of reflection equals the angle of incidence based on this perpendicular line. Now if I have a curved surface and I hit it, say, here, I have to draw the perpendicular at that surface. Like so. That's how a telescope works. Because a telescope has a mirror that no matter where you hit it, it's all going to go to the same point. Although I've drawn it not to scale. Most objects won't reflect all of the light. It'll reflect a percentage of the light. That percentage is called the albedo of the object. For example, ice has an albedo of 0.9, so it reflects 90% of light, whereas ocean water only reflects 30%. But this percentage depends upon the material as well as the wavelength of light. Aluminum, for example, in the optical reflects most of light, a lot of light. In the infrared, it absorbs most light. That leads us to plane mirrors. So if I have a mirror, like so, this is a plane mirror, it's a flat mirror. The angle that comes off and the angle in are the same. So if I look at the light as it scatters from an object and goes outwards and hits off of this mirror, and I trace these rays back to the mirror and keep going, because I don't know that the image in the mirror I'm looking at is actually right here. It looks like it's behind the mirror. And all of these lines all go to the same point, and that point is the image. So that's how we create an image. You have light reflecting off a surface that all looks like it originated from one single point. Now there are two different types of images. There are real images and imaginary images. If there is no actual light at the location of the image, we call this an imaginary image, because the image appears to be there, but it really is not. There's actually nothing there. Well, there's probably something there, but it's wood or fiberglass insulation behind the wall of your mirror, perhaps the next room. But there's clearly not light coming to you from that particular object. In this case over here, this is a real image because the light actually goes to a point, and I'm actually looking at that point to get a real image in this particular case here. All right, so hope you got all that. Now, this was a higher level class. We could go way more in depth, and we'd actually calculate what type of image you get and the image length and stuff like that. We won't do that here. The second thing that can happen when light hits a surface. Oh dear, I never defined what a surface is, did I? I made it sound like a solid object is a surface. Well, that's actually not the case. I mean, that's one example of a surface, but that's not the only example. A surface occurs anytime the speed of light or sound, the speed of the wave speed in an object changes. So if I have two layers of air that have two different sound speeds or light speeds, in those two layers, there will be a surface in between them. If I go from air to water, water has a different speed for light than air does, and that means that the surface of the water, where the air meets the water, is in fact a surface. So anytime I hit that kind of surface, whether it be air to air, air to water, etc., one thing that happens is you have light reflect off it. So light reflects off the surface of the lake. For example, sometimes you can see the background in the lake itself. It's always pretty. Some of that light is going to be transmitted. What that means is it's going to go through the surface. So some of the light, if I have light from air going into water, some of that light will be reflected, like so. Some of that light will pass into the water. We call it transmitted. Now, that theta the angle of refraction is now going to be a little bit complicated. I gave you kind of a pseudo equation for it previously in the semester. But this is what we call refraction. Light will be refracted into that substance. The third thing that happen is absorption. The light simply gets absorbed by that surface. Now, the percentage that gets absorbed depends on the substance and the wavelength. For example, water vapor is, water, if I have a cup of water, it lets optical light pass through it. It doesn't absorb very much light at all. Infrared energy, though, will be absorbed at very, very high percentages by that water. In fact, you can shine a light bulb through water, and you can see the light on the other side perfectly, but if you keep recording the temperature of the water, the temperature of the water will go up for some time because it's absorbing the infrared heat from the light bulb. And most light bulbs emit way more infrared heat than do optical heat. In fact, gases in our atmosphere that absorb infrared heat are called greenhouse gases. The Earth emits infrared heat, and so that heat gets absorbed by those gases. So that's one example of absorption. Water vapor is a greenhouse gas, carbon dioxide, nitrogen oxide, etc. Nitrogen is not, because nitrogen doesn't absorb infrared heat or optical light. Oxygen, O2, doesn't absorb infrared or optical light. O3 absorbs ultraviolet light, and that's the ozone layer. So those are the three things. Now, scattering is a subset of reflection. Now, I drew a very, very flat mirror. Unfortunately, nothing is quite this flat in reality, because if you look at an object at a microscopic level, it's not like this. It's more like this. I'm exaggerating quite a bit. But photons of light are insanely small. So they see this, they don't see that. And so when they hit the object, sometimes they hit in a good place, they can reflect it as normal. But if they hit somewhere else, say they hit here, it might get reflected straight back. Or at some weird angle. And so not all of the light will actually come back this way. It'll actually be scattered as a function with this will be the maximum peak, and you'll get light everywhere else. This, we call this glare sometimes. You can read the rest of it. There's some interesting stuff there I'm not going to talk about. And that's all I'm going to talk about scatter. It's just reflection, realistic reflection. Whereas the plane here is more of idealized reflection. So back to refraction. So we learned that the index of refraction equals the speed for light, equals the speed of light over the light speed in that substance. We also learned that if we have two signs, N1 and N2, and we call theta I as theta 1 and theta refraction as theta 2, then N1 theta 1 will be roughly approximate to N2 theta 2. Now this only works accurately, it's very, very small angles, but in this class, since we don't do sines and cosines, we'll have to just stick with that. But what that means is that if the index goes up, the angle has to go down. If the index goes down, for this to be a constant, the angle has to go up. So the angle is the opposite of the index. Index down, angle up. Index up, angle down. So that angle times index is a constant. By the way, the index of refraction also depends upon the wavelength of light, because if we say water, the velocity of light in that water depends on the wavelengths. Some wavelengths travel faster than others, and so that's going to create some very interesting things and very beautiful things that we see in nature. But this leads us to the critical angle. So if I'm leaving water where the index is higher than air, and I'm going down in index, that means the angle has to go up. Now, if I'm going from air to water, my angle gets smaller. So you can see that this angle is smaller than the angle that came in. But if I'm leaving the water at a very high angle, so this angle in here, we're going this way. If this angle is very high, and I need to get bigger by a factor of theta, and the theta between water and air, by the way, has an index of 1, approximately. That's the only one I expect you, actually 2 I expect you to memorize. Air and vacuum. I misspelled that. Also 1. I don't expect you to remember any of those. Water, though, is 1.4. So that means that this angle needs to be 40% bigger than this angle. Now, if this angle is too big, then 40% bigger than this would be greater than 90, which means you'd have to be greater than 90, and that would put you in here, which means that the light never gets to the air. It reflects off the surface. It doesn't refract. And so what happens is you have no refraction at that point, and you get what is called total internal reflection, which I still think is the kind of thing a supervillain would say. Okay. And no refraction. So why would this be important? How could we get good use out of this quirk of physics? Well, it turns out it allows us to see around corners, quite literally. We use this for, the biggest use for this is fiber optics. Fiber optic cables have very high indexes of refraction, so when the light leaves the cable, you're going down a lot in terms of index, and so the fiber optic cable can curve, in fact can take a 90-degree turn, and what will happen is the light will reflect and keep going down the fiber optic cable. And that's very useful for medicine, for internet, for a lot of other things. All right, now for something completely different. Yes, that's what I'm talking about. But still the same. Completely different, but still the same. Well, there's an oxymoron for it. Rainbows. So how are rainbows formed? Warning, a lot of scribbling on the board about it. Okay. That's more warning to me than it is to you. That's my cue that it's time to write stuff on the board. All right, so let's imagine a water droplet. Now I'm going to magnify the water droplet quite a bit, and I'm going to pretend it's spherical. It's not. All right, there's my water droplet. Now I have light that is white light. White light is the combination of all colors of light. This white light is going to hit the surface of the water droplet. Now at this point, the index of refraction changes, but the change depends on the wavelength. For some wavelengths, it might be 1.45, and some wavelengths, it might be 1.35. And the result is that the different colors, here we are going to go at different angles. So the blue might bend like this, and say red might bend like that. And then at this point, they can either leave the droplet and be bent again, and when they get bent back again, they'll be going parallel. But from your perspective, they could be coming from slightly different positions, and so in the sky you would see, the rainbow, like so, with all the colors in the middle. Sometimes, when it hits the far end, some of it gets reflected. And then it comes out. And my drawing's not very good here. When that is, you get a double rainbow. Now notice that the second rainbow will usually have colors in the opposite direction, and I haven't done it quite right. So usually what happens is you have internal reflection, it bounces off, it comes back. So maybe I'll do that. Okay, my drawing's still terrible. But what happens is that the order of the colors reverse. And so what would happen is you would see the second rainbow above it, like that. And double rainbows are actually quite common. I've seen quite a few myself. There's videotape of quite a few of them on YouTube. I have video that my wife has taken in all different places, such as Wyoming, Montana. I've never seen a triple rainbow. It is possible, but I've never seen one. The problem is that a very small fraction of this goes to this. And so a very, very small fraction goes to the triple rainbow, and it's just not bright enough to see with the naked eye. Usually you get the rainbow when you're looking away from the sun, so that the light from the sun hits the droplets and comes back to you. So that's usually how you see the rainbow, when you have the light source behind you. So if I have my sun back here, and I'm standing here, and there's some water drizzle over here, and I look this way, I will see the rainbow. If I like directly at the sun, not so much. Perhaps that's why we see rainbows after rain, because the sun usually is, well, I guess it depends where the sky the sun is. It would be on the opposite side of the sky from the sun, so I guess it doesn't really matter what time of day you get the rain. But that's rainbows. So to wrap up, we learned about what light does when it hits a surface or travels into another medium. And now we know how rainbows are created. Sorry for ruining rainbows for you. Physics teachers, we tend to ruin everything. No, not rainbows too. Oh. Now, one more lecture to go, and then we're done with lectures for this class.